All right, ready to go. Hi, everybody. Composable Security Architecture, Episode 2. So we have Bharat, Varun, myself. Pro is somewhere in the back. Very similar cloud to Caliptra. So 2 years ago, we did our first presentation on composable security architectures here at OCP, which was an attempt to sort of provide a framework on how to reason about and execute all these acronyms and protocols, etc. We scoped it to security critical devices, essentially handling user data in plaintext, NICs, accelerators, CPUs, and to some degree storage. We split, using the NIST terminology, we split the world into update, recovery, and measurement and attestation so that can help us better reason about the problem and separate the different mechanisms so that there isn't any confusion. We define requirements for TCB, and we try to align on several standards that we have been executing since. In other words, kind of try to provide a framework to make forward progress. The pictorial representation that we used 2 years ago at the end had some very deliberate ingredients into it, right? Of course, the CSEM, which is a very vibrant, robust OCP standard. You saw 2 presentations about it already today, very well aligned. The role of the BMC, the role of root of trust sitting there in the DCSEM as well. But one of the important things that we wanted to push was logically to physically TBD, out-of-band buses in order to perform these security activities using MCTP. One for talking to discrete roots of trust in charge of update and recovery using PLDM firmware update protocols to take care of platform availability. And another one using SPDM, and we saw the SPDM 1.3 presentation earlier today, to talk to roots of trust embedded into silicon SoCs to measure the quality of the boot, of the device that we have booted. So that was kind of the overarching idea. And put a pin in several contexts here because we're going to go through them and how they have evolved over the last 2 years. I3C, PLDM, SPDM, roots of trust that are both discrete and that are inside the package. So very top level summary of how it's going. TCG has adopted the reference integrity manifest. This underpins a little bit of everything else because it tells a verifier how to reason about a measurement. I3C is about to become a de facto standard. This is I3C MIPI basic 2-wire protocol, 12 megabits per second, royalty-free for everyone to implement. Ratified in SSD short, small form factors, and about to be ratified in PCI Chem 6. So it's something you can use to talk to out-of-band to your devices over the entire platform. USB 2.0 as well, 2-wire protocol, about to be ratified in PCI Chem 6. So you can also alternatively use it as an SPDM substrate. The NVIDIA HGX platform is the first publicly commercially available platform where you can touch an EROT, right? Servers and Titan are well-established concepts, but they're sitting behind the CSP boundary. This is the first one that you can talk to using SPDM and PLDM, and that you can buy if you have a big wallet. And of course, for the measurement side, Caliptra, right? Well, you all have heard Caliptra probably. We presented this a couple times over the last 2 years. It's essentially the block that sits inside the SoC and that is in charge of telling you the truth about the device provenance and the stack that it has booted. So this slide is something that we have presented before. We don't need to dwell. We're going to have several talks about Caliptra later in the day. Actually, the next talk is the main Caliptra talk, closing on 1.0. But I think the main message is that it's become a standardized open source specification and implementation of a root of trust for identity and measurement. And we're barreling down towards a 1.0 specification. The most important thing that we're going to emphasize here and talk about here in this presentation, it implements TCG DICE protection environment, DPE, which in addition to serving the original purpose of giving you a way to obtain SPDM measurements, it also integrates into the confidential computer architecture, both from the CPU side as a part of the HES and from the device side as a way to underpin the TDISP handshake protocol. So very quick primer on DPE. Jeff can do a better job, so if you have questions, ask Jeff. But basically, think of it as a stack, right? And you're pushing into this stack your measurements of the software stack that you're executing. So the DPE commands are very similar to the commands of a stack. You create a stack, initialize context, you can destroy it, destroy. Derived child is essentially the ability to push a frame into the stack or a measurement into the stack, or extend the measurement, right? So you boot out of ROM, you initialize your stack with your device identity, then you load your first piece of code, you push a frame into the stack, more. The cool thing here is that you can branch and you can create different contexts. Out of a common ancestor, you can go and start a context for the RMM, the confidential compute undervisor, the supervisor below the hypervisor. Or you can branch and you can create a DPE context for your UEFI stack, your traditional OS. The most powerful feature of DPE, though, because it's dice-based, that stack can become a key, can become a chain of certificates, giving you the information, the evidence about the nature of the stack, and a cryptographic key that you can wield it and sign it. And when you sign with this certified key, you're essentially providing an attestation. You're saying this statement is truth because it's bound to this software stack. So this is what Caliptra implements, right? So now I'm going to hand off to Varun to complete the concepts around confidential compute and around where we're going with update.
Thanks, Andres. This first slide is one of two examples of how Caliptra can integrate with confidential computing environments. This first example is on the ARM confidential computing architecture. CCA establishes a block called Hardware Enforced Security, or HES, and this is the block that's responsible for attesting to the platform. So in this example, you have the HES with a front end serviced by a microcontroller we call the SOC manager. This microcontroller can take the measurements during the boot process of the platform, say from the BL1 and BL2 components, and then stash those measurements into Caliptra. When a platform attestation token is needed in order to attest to the state of the platform for the realm, the SOC manager can query Caliptra to sign that platform attestation token using the DICE keys that has been derived from the measurements that form the TCB for the platform. The previous example was on the host side. This example is on the device side with the PCI TDISC protocol. In this design, there's a device security manager that's responsible for attesting to the TCB of the device. And here we have the same SOC manager component, this time implemented inside the device security manager. This implements an SPDM responder, and that responder would implement commands like get certificate, get measurements, and key exchange. The SOC manager's SPDM responder can rely on Caliptra to sign those measurements and key exchange updates so that it can be using keys that are wielded and a function of the SOC manager's TCB. You can also see a demo of this at the AMD booth in the expo where they have Caliptra integrated with SPDM responder. So that covers how Caliptra can be integrated in confidential computing environments. This next phase of episode 2 is thinking about how do we approach the root of trust for update and recovery. In episode 1, we talked about using external root of trust microcontrollers to abstract this functionality. In episode 2, we're taking a longer-term view and looking at the first principle problem, which is really that there's persistent state attached to the devices. That persistent state isn't really a requirement. It was just the most straightforward way of booting devices, having locally attached SPI flash. But now, with the advent of higher performance out-of-band buses that connect to a DC SEM and a platform root of trust, perhaps we can use those buses instead to push the firmware images to the devices and reduce the SPI flash fan-out. And if there are less SPI flash devices, or at least less devices getting updated, that's going to have less problems when it comes to root of trust from update. Last year, we talked about OCP recovery as a protocol for loading the first mutable code of a device over SM bus. So the thinking here is, why don't we just leverage that to build on top of it and continue the boot process of the device itself? In other words, we can make recovery equal boot. And we can use that to solve for 100% of the device's firmware and eliminate the RT-REC and the RTU problem entirely, make the devices stateless. The advantage of leveraging OCP recovery for this process is that it's an existing standard that devices should already need to implement for handling recovery for their flash-based boot processes. This limits the chicken and the egg problem because we're able to leverage existing investments. The other nice property of it is that with the push-based model of OCP recovery, it can simplify the platform design for the early boot. Now, the disadvantage is that that protocol is built over SM bus, it has a fixed sequence, and that's going to be pretty slow. You probably don't want to push the entire firmware over that interface. So instead, we're proposing a two-stage approach. You use the OCP recovery SM bus interface to push the early firmware, and that early firmware then implements an MCTP and MCTP-based flashless boot protocol to fetch the remainder firmware. And the nice property of this is that this is already the recommendation in the OCP recovery spec for handling firmware update of flash-based devices. You use the recovery to push your MCTP and PLDM Type 5 stack, and then you use that stack to do the firmware update. And now that you have MCTP up, you can use higher performance interfaces, I3C, PCIe VDMs, and USB 2.0. So this is how we get the ball rolling on these designs. In the future, we could eliminate the two-stage upstate as we work towards building optimized load paths, for example, bespoke hardware paths on I3C and USB. So here's a sequence of how you could potentially approach this for PCIe chem devices. The first step is the same as forcing recovery in a flash-based boot flow. You want to transition the device into recovery mode by issuing the force recovery command to the recovery controller, or alternatively, you just erase the flash and it'll boot up that way. Once a fundamental reset is asserted to the PCIe device, it's going to reboot and thereby enter the recovery mode due to the previous state. From here, the platform can use the OCP recovery interface to push that early firmware, all while keeping the PERST asserted so that you don't have any dependencies on PCIe link training. In the third step, the PERST gets deasserted, the early firmware is already loaded, and now the PCIe and MCTP fabrics can be initialized and enumerated. And from there, those fabrics can be used to fetch the remainder of the firmware. Now, once the remainder of the firmware is used, the device is functional. So now if I took Microsoft Paint to the previous diagram, here's what we end up patching up. Instead of a generic block for attestation, introducing Caliptra. Instead of a discrete external router trust for update and recovery, a flash bliss boot endpoint on the devices. And then a flash stream protocol, and potentially as PLDM Type 5 itself or something else. And then for out-of-band buses, I3C, and also the option of USB 2. For next steps, for Caliptra, the most imminent one is 1.0, and you'll see the status of that in the next talk. For flashless boot, we're in the earlier stages of the project. One of the first questions is to define the flashless boot protocol. The simplest answer could be PLDM Type 5 itself. It's what devices already need to implement, and it has the requisite functionality, basically a command that lets a device fetch more firmware. Instead of writing it to flash, you write it to your RAM. And then challenges for flashless boot itself. We have to model and prototype to say, is the two-stage strategy sufficient for boot time? Do devices have enough memory to handle holding all of this firmware at once instead of potentially paging or relying on flash as a backing store? What is the load on BMCs and platforms itself? One approach that we were thinking about this is limit the flashless boot flow to just the cold and warm boots of the platform so that the behavior towards the BMC or PA rot is always deterministic. You don't have to handle partial resets of the device. The device should handle that on their own. But that increases the load for the device. We know this is also going to be a transitory thing because this is a major architectural change. So how do we handle the mix of device capabilities? One angle could even be that we have devices like flashless boot bridges. They could implement the flashless boot protocol on one side and emulate a SPI flash on the other side. And then how do you handle manufacture and testing? Ultimately, when vendors are building products that are on standardized boards like PCIe Chem or at SFF, they need to handle environments that could be flash-based or flashless. And so one of the advantages of building off a recovery approach is that you don't actually have to erase or eliminate the flash. You can just force the device to not use it and then attest to the fact that it didn't use the flash. And our call to action as we move towards the data center architecture of the future, in the short term, implement Caliptra and OCP recovery. This is going to be helpful for the platforms of today. And then tomorrow, work with us on working on improving and implementing Flashless boot. Thank you.
So I got a question. So I don't quite understand flashless boot. And so where is the boot code stored? And I mean, it's not an eMMC, it's not NOR flash, it's...
Yeah, and this problem can scale to many levels. There's turtles all the way down. The first level that we'd want to talk towards this is how do we address it for peripheral devices? That has the highest bang for buck because that's the most diversity of devices and associated update paths, which then cause problems for hyperscale service providers that need to deploy these devices. So if we eliminate the use of flash from booting these devices, a device upstream, like the platform root of trust, for example, that could have the flash that holds the firmware for everything. And it and the BMC together coordinate the boot process at the start.
I see. Okay, thank you.
Just to add one more comment to that, one of the things that you may have heard about is seamless, impactless, hitless with different names. And if you think about it, we want to patch the systems out of band through the BMC, and that's been our CSP use model for a while. And this naturally fits into the future model because it's not just the seamless, it's also the boot time we go through the same exact flow. Yeah, it is possible that we don't even have a flash per se. We may have a temporary storage device that we deploy whatever firmware that we want from a central entity to say, I want these clusters, these nodes to have this particular firmware that I know that I will trust. And that particular flow will be the same independent of if I'm doing it boot time or impactless time.
I was curious, in the flashless boot, are we creating a new vulnerability from the mutability of the running firmware now being in DRAM and not in flash?
It's a good question. And I think the answer to that is there is always a time of check to time of use issue with devices having firmware in flash. And so that's where we build specs like OCP Secure Boot, OCP Attestation, because what matters is the execution context on the device itself. And so there may be devices that are paging from flash, paging from RAM, directly loading from RAM. Ultimately, it's about what are the trust boundaries attached for an enclave, and what are the assertions that you're attesting towards.
I will note that there are some devices out there that do have a surplus of flash.
Absolutely.
So from the flashless boot perspective, looking at a hot plug device that could be different than the devices that are currently in there, what is the flow for making sure that your platform root of trust has, I mean, you can't have every single flash that you have in your entire data center. Is that something that you then have a flow that it goes and fetches that once it's hot plugged and then determines what device that is?
Hot plug events are not unplanned events in the data center.
Right, so you would go ahead of time and load the firmware to your platform root of trust, those
Correct.
systems, and then hot plug the device.
Not just the firmware, also the expectations. This is what we want to see measured once it boots. And then if it didn't measure the way we wanted it, we have a problem.
Okay,
So
thanks.
it's both things. Or put differently, hot plug events in the data center that were not planned are extremely suspicious.
Yeah, and actually I'd say, right, there's a big difference between hyperscale and enterprise, I think.
Of course,
So
of course.
in lots of other environments, it might be a non-planned event, right? You have a failure, you hot plug into a device, And so you may not have coordination to kind of preload everything into that server that's needed. But yeah, I think there's just different use cases maybe.
I would argue, though, you shouldn't be surprised by hot plug events regardless of your environment.
Customers, right, that are not as organized as hyperscalers, I would
Yeah,
say.
understood, understood.